Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be continuing our discussion of rotational dynamics by discussing the interaction of torque and angular momentum. You will recall that in our previous videos we discussed and defined such terms as torque, which was defined as R cross F, and the angular and linear momentum. So I'm just going to say momentum, and I'm going to kind of branch it into linear momentum and angular momentum. And those were defined respectively. P is m times v, and L is R cross P. Finally, you will recall Newton's second law. So we have Newton's second law, which again we can break into linear and rotational version. And in the linear version, we wrote originally that the sum of forces is mass times acceleration, and for rotational we wrote that the sum of torques is moment of inertia times angular acceleration. However, we also have modified the linear version to say that a more general version, sum of forces, is not just m times a, but is actually the rate change of the linear momentum. Now, looking at this set of equations, all of these equations that I've written, it may not be obvious to you, especially if you're taking just like Physics 1 and you're new to physics, or most of a semester into being new to physics. But I have here a torque, which is an R cross F. I have an angular momentum, which is an R cross P. I have a force, which is a delta P delta T. I can easily imagine saying, okay, let's recast this, and this, basically all four of these equations, and see what comes out. So if I'm looking at what's the sum of torques, I'm basically looking at the sum of R cross F's. And as long as I am able to sort of move the R outside of the sum, as long as this is associative, in other words, I should be able to write R cross sum of F. But that's just the same thing as R cross delta P over delta T. Now this may seem a little bit dodgy that I've done here, and it is, because not all forces being applied to an extended object satisfy this. But in looking at the basic equation that I've got here, this looks kind of like what I'd expect a change in angular momentum to be like if I had a fixed radius. Okay, put differently, this looks like the I times alpha version of an angular momentum change. So I should be able to generalize it. So basically our generalization says that instead of saying, okay, everything's at a fixed radius, what if the radius can also vary? And so I expect for this term, rather than to be delta P delta T, to maybe look like a delta of R cross P over delta T. But that's just the same thing as the rate change of angular momentum. So my generalized version says that the sum of torques gives me the rate change of the angular momentum. Now, this in and of itself is kind of neat, because now we see we've kind of come full circle, if you will, with this equation. Because originally when I introduced angular momentum, I said there must be something that is being changed by a torque beyond just the angular speed. And that was a sort of argument from symmetry, or maybe from analogy to this Newton's second law for linear momentas. So the conclusion that we might say here is forces change linear momentum and torques change angular momentum. So if I apply a torque to an object, then I expect to get the object's angular momentum to change, if there's a net torque, that is. So now we come to one more thing that we can discuss about this, which is what happens if I have a collision between two extended objects, or even between one extended object and one non-extended object. So let's consider now what would happen if we had two objects which collide with each other that are kind of extended objects. I'm not going to go through all of the math on this because I'm trying to make this a relatively short video. But let's say that I happen to have an object, say right here, and I have another object, maybe like a disk or something, that is going to move and collide with this first object. Maybe we're on a frictionless surface. So let's think about what's happening here. At the moment when the two collide, I have essentially like a stick or whatever this is, and I have a disk that has collided with it. And I could ask how much torque is being applied on each about some axis of rotation. Maybe we pick an axis of rotation to be here, for example. If this is my axis of rotation for the system, then the point of impact would have radius r, and that's true for both the stick and for the disk. Now let's draw in our forces. So this one impacts and has a force in this direction. So let's call this force stick disk. And by Newton's third law, I have up here the force of the disk on the stick. Okay, and Newton's third law says that these two will have opposite direction but equal magnitude. In other words, FSD is negative FDS. Okay, so that right there is linear momentum conservation, comes out of that, assuming again that there's no other forces acting on the system. So these are both free to move. Now if the stick is nailed down or like allowed to pivot about a peg or something like that, like if this axis of rotation represents a hole that there's a peg in, then this basically means that there's an additional force on the stick from the peg, or could be an additional force on the stick from the peg. So, you know, you may end up not getting linear momentum conservation in that case, but as long as this is free to move and this is free to move, not just to rotate but also to slide, then linear momentum should be conserved here. But we also can now look at the torques. So I have a torque that's being applied to the disk by the stick, and that should look like R cross with force disk stick. And then on the disk, I have a torque on the disk that's being applied by the stick, and that should look like R cross force stick disk. Since these two forces are, by Newton's third law, opposite and equal, you end up being able to rewrite this as the cross product R cross F disk stick. And so in other words, that means that the torque from the stick on the disk is the negative of the torque of the disk on the stick. So the implication of this is that if you have a closed system with objects that interact with each other but no external forces, then not only might linear momentum be conserved, angular momentum should be conserved. So let's write that out. This implies conservation of angular momentum, at least for a closed system. And by this I mean, of course, this statement that these two torques are opposite and equal. So now we're up to 3 conservation laws for a closed system. We now have conservation of energy, or mechanical energy. So this basically says that initial kinetic plus potential energy should equal final kinetic plus potential energy, assuming no work has been done on the system. Second, we have linear momentum. And linear momentum basically says that the sum of all the initial linear momenta should be equal to the sum of all the final linear momenta. And these are summed over the index j. And 3, we also have angular momentum. So angular momentum conservation basically says that the sum of all of the initial angular momenta of the system should be equal to the sum of all the final angular momenta of the system. And the stipulations that go with these are that no outside work is done for the first one, so no outside work. The second one is no outside forces, net outside forces. And the third one is no outside torques. All right? So we can work a quick example to close out. All right? For our example, we have a wheel on axle. This is a fairly heavy wheel, so maybe it's like a stone grindstone or something, and we're applying to it a torque in one direction. We could say T applied, which is 60 joules per second. That's tau applied. And in the opposite direction we have a friction torque, tau friction, which is 36 joules per second. And we want to know if this is done for a time of 4 seconds, then what will be the final speed of the wheel, the final rate of rotation, which we could interpret as angular speed. So what we want to do is note that the sum of torques should be the change in angular momentum, delta L over delta T, and therefore we can write something like tau applied minus tau friction is rate change of the angular momentum. And so our angular momentum final should be this difference in torques times the time. Making use of the fact that L is equal to I omega, we can write that delta L is I omega phi minus omega n. It follows from this that we can solve for the final by dividing both times by the momentum. Alright, so now we plug some numbers in. Omega final is torque applied, which was 60 joule dot second, minus the friction, which was again 36 joule dot second. So we got 60 minus 36 joule dot second divided by 12 kilogram meters squared times 4.0 seconds. So again, using the numbers that we've been given here. This comes out to a final angular speed of 8.0 radians per second. And that's it. Okay, so that was our example for this video. I think on that note, it's time to end the video. We don't want to make it too long. So hopefully you've learned something from today's video. That is all for today. Thanks for watching.